This is 10.3, day 2, and we're going to be graphing polar equations. And we're going to start with y equals 4 sine of theta. Now, the rule that I've kind of come up with is you take the coefficient of theta, which is 1 here, and we're going to multiply times 2. And that's 2, of course. And we're going to count by pi over 2's in our chart. So we have theta, and then what r would be when we plug theta in for the values in for theta. And we're going to count by pi over 2, and we're going to go to 2 pi. Actually, with circles, we only need to go to pi. So 0, pi over 2, and pi. Because circles finish in pi. So we have to go from 0 to pi. Now, whoop, I closed it. If we plug 0 in, 4 times sine of 0 is 0. If we plug pi over 2 in, that's 1, so we have 4. And then if we plug pi in, the sine of pi is 0, and we're back to 0. So all we have really is 2 points. 0, pi over 2 is 4, and then pi is back to 0. But we know this is a circle, and we know that's a circle with a radius of 2. So we just have to draw now a circle with radius of 2, and I'll draw the best circle I can. We'll call that good. Now we have negative 5 cosine of theta, and we're gonna double this coefficient right here, 2, and we're gonna count by pi over 2's. But I also know that, cosine goes along the x-axis. So I'm not gonna make a chart for this one. I think I'll just kind of work it out here. We know we have a diameter of 5. And so the radius is going to be 2.5. Here's 3. 2.5 is right there. So we'll go up 2.5. So about right there. And down 2.5. So 2, about right there, let's say. And we have this circle right there. So that's negative 5 cosine of theta. Here we have cardioids. Now let's go by the same rule. Let's take this 1 times 2, and we're going to count by pi over 2. So now I know 1 times 2 is 2, but that goes right there. But cardioids, you have to go from 0 to 2 pi to complete a cardioid. And we're going to count by pi over 2. So we have 0, 1 half, we get 2 halves, 3 halves, and then 4 halves. Now when we plug 0 in, sine of 0 is 0, so we have 3. Now this is the r. Pi over 2, sine of pi over 2 is 1, so this is going to be 6. Sine of pi is negative 1, so that's going to be 0, because you end up with 3 plus 3 sine of pi. Sine of pi is, oh no, that's going to be 3. I got it. Good thing I checked it. 3, 6, that'll be 3. And then 3 pi over 2, that's the one that's going to be 0, because we have 3 plus 3. Sine of 3 pi over 2 is negative 1. There's the 0. Then 2 pi is back to 3. So 0 is 3. Pi over 2 is all the way up here to 6. And then pi is 3. 3 pi over 2 is 0, and then back to 3. So here's what the cardioid looks like. We can do this. It's kind of rounded. It touches the pole because our smallest value here is 0. This is where it touches the pole. And then goes through, oh boy, and then is kind of rounded like that. So there's a cardioid. Here's a limacon with an inner loop. Limacon with an inner loop. Let's double the coefficient just like we do every time. That's 2. And so we're going to count by pi over 2's. And really what we want to end up doing is plugging in values that are pi over 2's. So we have theta and r. 0, 1 half, 2 halves, 3 halves, and then 4 halves. And limacons you got to go from 0 to 2 pi to finish those. So when we plug 0 in, cosine of 0 is 1. So we get the -1 right away. That's what causes what we call this inner loop. Cosine of pi over 2 is 0, so that's 2. Cosine of pi is -1, that's 5. Cosine of 3 pi over 2 is 0, so that's 2. And then 2 pi, that's back to that -1. So when we're at 0, we're back here at -1. Pi over 2 is 2. Pi is 5. That's back here. 3 pi over 2 is 2. And then we're back to -1. So here's how these graph. They go wider than this. They do go through the pole, loop around. There's the inner loop. Back through this one right here. And then it finishes. There's a limacon with an inner loop. A dimpled limacon. Dimpled limacon. Well, let's take this coefficient. We're going to multiply times 2. That's 2. And this one we're also going to count by pi over 2. So far everything we've been counting by pi over 2, and that's going to change a little bit for the roses. This is the theta, this is the r. So 0, 1/2, 2/2, 3/2, and 4/2. Now we plug 0 in. Sine of 0 is 0, so that's 3. Pi over 2 is 1, that's 5. Pi is 0, that's 3. 3 pi over 2 is -1, so we get 1. And then 2 pi is back to 3. Now notice, none of these are 0, and none of those are negative. So this one never touches the pole. It never goes through the pole. So 0, 3. Pi over 2 is 5. Pi is 3. And 3 pi over 2 is 1. Right there. So this loops around like this, and then loops around like that. It's almost, it's similar, I guess, to a circle, well, but it's dimpled. So we have to dimple it right here. Boom, dimple. Yeah. For sine of 2 theta. Well, let's take this. Here's where we're finally going to get something other than 2. We're going to take this. We're going to double it. That's 4. So on this one, we're going to count by pi over 4s. And so what ends up happening when you plug these pi over 4s in, the pi over 4 will get multiplied times 2, and we're really going to be evaluating multiples of pi over 2. Now when 2 is even, then we have 2 times 2 petals. So we have 4 petals. That's what we're going to expect, 4 petals out of this. And so if this was a 4, we'd expect 8 petals. If this was a 6, we're going to graph 12 petals. When this is even, they graph from 0 to 2 pi. So let's get the chart. Where should we put it? Should we put it over here? Let's go theta and r. We've doubled that coefficient. We're going to count by pi over 4s, and we got to go all the way to 2 pi. So r. So we're going to go 0, 1/4, 2/4, 3/4, 4/4, 5/4. I gotta keep going. 6/4, 7/4, and then finally 8/4 is 2 pi. But I got good news for you. We don't have to plug values in for all of these because there is a pattern when you follow this pattern. When you count by pi over 4s, there ends up being a pattern. So let's see what we get when we plug 0 in. Sine of 0 is 0. And then if we plug pi over 4 in for that theta, we get sine of pi over 2, which is 1. So that's 4. Now, you can keep plugging in values if you want, but here's the pattern. Every other number is going to be 0. And then every other number alternates 4 and -4. So this will be a 0. This will end up being -4. This is 0. -4, not -4, +4. Let me erase that because it alternates signs. 4, 0, -4, and then 0. So that's the pattern when you count by pi over 4s when it's 2 theta. So 0 is 0. Pi over 4 is 4. So we got to go 2, 4. There it is. Pi over 4, 4. And we've done half a petal. It loops around like this. Pi over 2 is back to 0. So when we get to pi over 2, we're back to 0, and we've created 1 petal. 3 pi over 4 is -4. That's down here. Down here. Pi is 0. So pi is 0, like that. 5 pi over 4 is 4. So then it loops around over to here. 3 pi over 2 is 0. Back to 0 when we get to 3 pi over 2. 7 pi over 4 is negative 4. So that's up here. There's this half of the pedal. And then 2 pi is back to 0. And we got the 4 pedals of the rose. This is an odd number. 3 is an odd number. So we only have to graph this from 0 to pi. This one finishes in pi radians. You don't have to go all the way to 2 pi. All right, well, we're going to double this coefficient so that we get that everything we evaluate ends up being pi over 2. So 2 times 3 is 6. We're going to count by pi over 6s. So like I said, everything ends up being a pi over 2 when you evaluate it. So we have theta and r. But we only have to go to pi. 0, 1/6, 2/6, 3/6, 4/6. Run out of room. 5/6 and 6/6. Now the pattern stays the same. We just have to know where to start the pattern. Sine of 0 is 0, so 0. When we plug pi over 6 in, we're evaluating sine of pi over 2, and that's 1. So 4, 0, negative 4, 0, 4, 0. So the zeros, every other one is 0, and every other one is a 4 or negative 4. 0 is 0. Pi over 6 is 4. Pi over 3 is back to 0. So we go half a pedal. And when we get to pi over 3, we have the other half of the pedal. Pi over 2 is negative 4. That's down here because pi over 2 is up here, but we're going negative. So there's another half pedal. 2 pi over 3 is back to 0. So we're back to 0 and we're at 2 pi over 3. 5 pi over 6 is 4. That's right here. So then we have a half a pedal there. And then when we get to pi, we're back at 0, and that completes the rows. Here we have cosine. So let's count by pi over 6s. Theta and r, 0, 1/6, 2/6, 3/6. I'm going to run out of room. 0, 1, 2, 3, 4 pi over 6, 5 pi over 6, and then 6 pi over 6 is pi. So cosine of 0 now is 1, so this starts at 4. When we plug pi over 6 in, we get pi over 2, that's 0. So 0, negative 4, 0, 4, 0, 4. So 0 now we start at 4 instead of starting at 0. When we get to pi over 6, then we're back to 0. So we have a half a pedal there. Now we expect 3 pedals, by the way, because this is odd. I don't know if I said that on the last one. The last one up here, when it's odd, we expect the same amount, so 3 pedals. The same amount as the coefficient right there. All right, so 3 pedals on this. Pi over 3 is negative 4. So pi over 3 back here at negative 4. Like this. Pi over 2 is 0. 2 pi over 3 up here is 4. That's probably a little more curved than that. Something like that. 5 pi over 6 is back to 0. So we got 5 pi over 6. And then pi should be negative 4. That wouldn't have fit the pattern. Pi would be negative 4. So pi back to negative 4, and that puts us right at the beginning. Area of a sector. The area of a sector OPQR, let's say it's a theta radians, over the area of a circle is 2 pi. So if we say the area of a sector is A, that's what we're looking for here. And then the area of a circle is pi r squared. Now if we cross multiply, you get area is, we multiply this over here, the pi's will cancel, and then you have 1/2 theta r squared. So that is the area of a sector. Find the area of a circle, r equals 4 cosine theta, using calculus. Hint: the polar graph completes the circle in pi radians, which means that we're going to integrate the area. Find the area. We're going to integrate we end up integrating this right here. So we're going to integrate from 0 to pi to find the area of the circle. We're going to go 1/2 r squared. Well, this is r right here, which is 16 cosine squared theta, d theta. And the theta ends up being the d theta right there. That's the same thing. All right, well, the problem is we don't know how to integrate cosine squared. So we have 8 integral from 0 to pi of cosine squared theta d theta, but we can integrate cosine of 2 theta. Cosine of 2 theta is 2 cosine squared theta minus 1. So if we add over 1, we get cosine of 2 theta plus 1 equals 2 cosine squared theta. Now we're going to divide by 2. So we're going to replace cosine squared theta with 1/2 plus 1/2 cosine of 2 theta. So let's make that replacement. So 8 integral from 0 to pi of 1/2 plus 1/2 cosine squared theta d theta. Well, we can factor out a 1/2 and make this 4 integral from 0 to pi of 1 plus cosine squared theta, not squared, 2 theta, 2 theta, d theta. So we have 4, we got theta, what would we have? We'd have plus 1/2 sine of 2 theta from 0 to pi. So 4 times pi plus 1/2 of 2 pi is 0. And then if I plug 0 into both of these, we get 0. So it ends up being 4 pi. Graph each and find the intersection points. So this right here, we're gonna count by pi over 2's. So cosine of pi over 2, because we're going to double this coefficient right here. I'm going to count by pi over 2's. Well, cosine of 0 is 1, so we get 0. Cosine of pi over 2 is 0, so we get 1. Cosine of pi is -1, so we get 2. And then cosine of 3 pi over 2 is 0, so we end up with 1. So it looks like this. It is a cardioid. It bounces like that. And then r equals 1. Well, that's a circle. Circle with a radius of 1. That's right there. So we're asked to find out where they intersect. Well, it looks like they intersect at pi over 2 and 3 pi over 2, but we can, do this a little bit more mathematically. We could probably figure it out using the graph. So 0 equals negative cosine. We're setting them equal to each other because they both equal r. So cosine of 0 is equal to, cosine of theta is equal to 0. So theta is equal to exactly what we thought, pi over 2 and 3 pi over 2. And that means it's intersecting up here and down there. All right, how about 3 sine and 3 cosine? So 3 sine is up here. So we have up here at 3 and 0 with a radius of 1.5. So 1.5 is right there. So 1.5, about right there. And 1.5, let's say right there. So we have this circle right there. And then 3 cosine, as we have a diameter of 3. 1.5 is the center, so it must intersect something like this. Well, it's intersecting at pi over 4. But we want 3 sine of theta equals 3 cosine of theta. And we can divide both sides by 3. So we get, where does sine of theta equal cosine of theta? Well, that happens at pi over 4. But if we divide by, what do I want to divide by? I want to divide by cosine. So 1 equals sine of theta over cosine of theta. So that 1 equals tangent of theta. And if we do inverse tangent of 1, then that's where we get the pi over 4. So that's the intersection point.